Hello, my name is Stephen Carell. I will be doing the presentation on the study carried out titled Identification of Driver Phone Usage Violations via State-of-the-Art Object Detection with Tracking. So to give a bit of background and motivation behind this project, according to the World Health Organization, 1.3 million people die each year as a result of road traffic accidents. Drivers using their mobile phones are around 4 times more likely to have a crash in comparison to drivers who do not. And typically, capturing a driver using the phone is quite a laborious task. It would often involve, say, a police officer or roadside patrol having to physically witness the violation as it happens. So a result of that would be potentially missing a lot of violations. In recent years, it's seen the development of object detection in video surveillance. So, typical uses for this technology would be airport security, where they would use object detection to make sure nobody has left a bag unattended, or it could be using for people counting, or could be loitering, just to name a few. For this study, we proposed 2 deep learning approaches to automate this process. The first approach is the single step. So this will detect the mobile phone from one full big image. So within that image, it will search for that small object, which is the mobile phone. So because it's just a one step, it would be faster. However, it would be a trade-off with accuracy because you're trying to find such a small object within a large image. So the second approach is the two-step, which addresses the accuracy issue. So this would first, it's 2 models which would run simultaneously. The first model will detect the windscreen, and then that will be used as an input for the second model, which would then detect the mobile phone. And then finally, a tracking algorithm is going to be integrated to log unique detections and take snapshots of set violations. So it's very important that it's able to log unique detections because we would need to distinguish between frames. So what you wouldn't want to happen would be having 10 frames of one violation, but the detector counting that as 10 separate violations, then outputting 10 images. We don't want that to happen. We need it to identify between each detection, and the tracking algorithm would allow us to do that. So one of the first steps of this project was a feasibility study to see if we were able to obtain good enough images with a camera through a vehicle windscreen that we deemed good enough that an object detection system could detect small objects. And to do this, we tested a range of both high-end and low-end cameras. So the 2 cameras on the left are what we class as the high end, and then the one on the right is an off-the-shelf, low-quality Chinese camera. And then to give you an idea of the difference between them, if we look at the images on the right here, we can see that the top images are taken from the high-end cameras, and you can see that's even when zoomed in, it's a good enough quality image. And then the bottom image is taken with the low-end camera, exact same setup, exact same distance, weather condition. The only difference is the camera, and then you can see the huge difference that makes. So for this study, it's important that we are able to train and develop a system that is able to handle both quality of camera. And the next issue was addressed from a previous study where they were able to detect mobile phones, but they were not able to do it during certain times of the day due to windscreen glare. So we were able to solve this issue by using a polarizer filter. So we can see the low-end camera and the middle high-end camera. There's a polarizer filter attached to the end of the lens there, and what this would do is it would allow us to eliminate, well, certainly significantly reduce the windscreen glare. So if we take a look at this image here with the red car, top image is without a polarizer filter, where we can just about make out there's a person, but we can barely see if he's using his phone. And then the bottom image is the same image, but with the polarizer filter. And what we've done is we ran that through a YOLO object detection system with just its standard weights where it would detect a person, and then the top image it's not able to detect, and the bottom image it's able to detect with 91% accuracy. The next challenge that we addressed was nighttime images. So it's very important, a system like this, that it's able to detect with high accuracy 24 hours a day. And to do it at nighttime, we would need to look into the type of infrared used. So we explored a couple of different types of infrared, 730 nanometers and 850 nanometers. And upon testing, we concluded that the 730 nanometer was a lot better at penetrating windscreens, and we can see an example of that in the image here, where we can clearly see the driver through the windscreen. So the chosen object detectors and base models are listed in the table here. So for the object detectors, we chose both YOLO V3 and V4, faster RCNN, CentiNet, and SSD, as well as a range of backbones and image resolutions. It was very important for us that we tested a large amount of object detectors in order to come up with a good conclusion as to what would work best for such application. One of the most important things on this project as well was obtaining the correct amount as well as the correct type of training images. So we can see an example here with the 6 images as a little snapshot from our training data. We have different quality images as well as under different weather conditions, and we have a range of RGB and black and white images. And the object detector that we trained, it was very important that it would not just perform under, say, good conditions, good camera. We wanted it to perform, like I mentioned, 24 hours a day under multiple weather conditions. The vehicle images on the right there give an example of this. So the top 2 images are using a high-end camera, bottom 2 images are using a low-end camera. The left 2 are taken under good weather conditions, and then the right 2 are taken under dull overcast day, and we can see the difference that makes, especially with the absolute worst case scenario of a low-end camera and not ideal weather conditions. So it's very important that we train a model that would detect all of these with a reasonable, very high accuracy. In terms of the number of training images, so the single step approach would be trained first on, it would be trained also, on license plates. So the license plates would be used as a means to count the number of vehicles. And they were obtained quite simply through an open source database. The 2-step approach would first detect windscreen, where we had almost 500 windscreen images, and then with regards to the mobile phone, on the second part of the 2-step approach, we trained with 2,154 images, but 1,700 of them were the bespoke images as discussed and shown here. So just to give you an idea of the time it took to take and obtain that amount of images, it was quite challenging, but we got there. So now taking a look at the results, there is, as you can see, quite a lot of data in this table, so I'll just summarize. In terms of accuracy, the YOLO models, all of them consistently performing a lot better than the rest of them. And with regards to frames per second, also performing very well. The accuracy metrics that we chose to use for this study was average precision, and then we tested with both an IOU threshold of 0.5 and also 0.10. And if we look at the image here, we can justify that an IOU threshold of 0.1 is probably more appropriate for this application, because we can see that when it's set to 0.5, it's missing this violation, and when set to 0.1, it's capturing it, and we can say it's doing the job it should do. But I think because the images it's trying to detect, the objects, have got so much variation, it's very difficult to have that very high IOU threshold every time. In terms of the two-step and one step. This is representing the one-step, single-step approach, and this is the two-step. And we can see the accuracy is a lot higher on the two-step. And then an example here is the same frame. First one with the single step approach is not capturing the violation, and the two-step is. So we propose the two-step approach, and we can see some output images here where the lower quality images, the lower end cameras, are getting a lot of false positives. So we also propose to increase the threshold of what accuracy it will output from 0.3 to 0.6. And last but not least, the final model chosen was the YOLO V3 with the small resolution, because in terms of accuracy it's very close to the higher resolution ones, but the frames per second is significantly higher. So an application like this, it's very important that the speed which the model runs is very fast. So the final results with the chosen model, it's getting frames per second for detection of almost 30. Add the tracking, it's losing a little bit of it, but with the two-step approach, it's dropped quite a lot because it's having to run two models simultaneously. And in terms of final accuracy, what we done is we split the data, the test images, from high-end and low-end cameras. So we can see with the low-end worst-case scenario, we're getting 74% accuracy, and with the high-end, almost 96% accuracy. And applications such as this, where they would be using traffic cameras on a public road, would typically use the high-end camera. So realistically, this would be what kind of results we can expect. And then here's a little example of an output image. So this is what the system would automatically output and save in a daily folder. And just to finish off this presentation, I'll quickly play some video clips showing the system in operation. And that brings us to the end of the presentation. So I now invite any questions that anyone may have. Thank you.